So I'll introduce to you today liquid crystals as an intermediate state of matter between crystalline solids and isotropic liquids. And so the simplest type of liquid crystals, this nematic liquid crystal fluid, is composed of rod-like building blocks, such as molecules, that have orientational ordering along the director, which is average ordering direction. And therefore, you have anisotropy combined with fluidity. So just like isotropic liquids, this liquid can flow, yet it has anisotropic properties similar to that of solid crystals, where differently from liquid crystals, we would have both orientational and positional ordering. Right, so in a solid crystal, we can reproduce the entire material by simply translating these building blocks in space, as depicted in here, right? Because of both positional and orientational ordering of this system. So the liquid crystals are therefore an intermediate state of matter that combines the properties of isotropic fluids and anisotropic solids in a very unique way, which allows us to use them very extensively in different types of applications. The very classic example of liquid crystal molecules is shown in here. It has a chemical structure of two benzene rings, right, connected to each other. And on one side, you have this CN triple bond and the hydrocarbon chain on the other side. So the chemical structure is a bit more complex than, as physicists, we would often approximate it with rods, as depicted in here. But for many properties that we will discuss, this is sufficient. Because a rod, just like that face of nematic liquid crystal, has a uniaxial symmetry. And so, as I already mentioned, in liquid crystals, unlike in crystalline solids, we have no positional ordering. So you can see in here these little rods representing molecules or colloidal particles forming the liquid crystal, being oriented in the same direction, but once you would remove the rods themselves and only look at the centers of mass of them, you would see them being disordered, right? Moreover, over time, these centers of mass move around and the fluid can flow, right? So they are not in their well-defined stationary positions as they would be in a crystalline solid, right? Such liquid crystalline states of matter can be formed by a very large variety of building blocks, ranging from the small molecules I was already showing, this biphenyl and here in a different presentation, to DNA, to microtubules, to tobacco mosaic viruses, and many, many other types of nanoparticles of both synthetic and biological origin. And so such anisotropic liquids, as you can see in here, can have the properties of crystalline solids, which in this case would be optical properties of birefringence when we look at them between a system of two cross polarizers. So if you have an isotropic liquid like water, between two cross polarizers, you would see no light passing through, right? It would be all extinct. However, when we place a jar of a liquid crystal in between a system of two cross polarizers, light is coming through. Moreover, it's coming through with this pattern, this texture that you can see. And this is because the liquid crystal is changing polarization of light. Therefore, the second polarizer is not able to extinct it, right? So as I already mentioned, however, a very large variety of building blocks can form such materials. So with the ones in here being just examples. So the example that I showed you is perhaps the most widely known, the nematic liquid crystal, most widely used in all different types of applications, from our displays of laptop computers and TVs to all kinds of electro-optic devices. For example, we use in laser tweezers or electro-optics, or in shaping femtosecond laser beams, right? They have many different applications. But actually, when liquid crystals were discovered and people did not know what is their structure, one of the very original proposals was coming from Max Born, whom, of course, all physicists and perhaps everybody knows very well. So he was actually developing a model of this liquid crystal as being made of molecules that behave as molecular dipoles. So, for example, indeed, a molecule, as I was showing you from the very beginning, this pentyl cyanobiphenyl does have a molecular dipole in here, right? However, in the phases that people studied for over 100 years since his time, this was his paper, right? Could only find the phases where these molecular dipoles would point in all antiparallel directions. And even though the molecule itself is not a perfect rod, I already told you, the symmetry of phase is uniaxial and non-polar, because there is an equal number of little molecular dipoles pointing up and downwards, right? And so in a similar way, starting from 50 years ago, people were dreaming about other types of phases that would be of low symmetry, yet can flow, right? And an example of these phases is this biaxial nematic that you can imagine being formed not of rods, not of little dipoles, but rather of bricks. And these bricks, while being able to move one around each other, would orient on average the longer and shorter axis in the same directions that would be described by mutually orthogonal directors, right? For a uniaxial liquid crystal made of these rod-like molecules with the infinity symmetry, we have just axis of ordering described by this average direction director. In here, we can define multiple directors that are orthogonal to each other. And this phase was very hard to find until recently. It was even called the Higgs boson of soft condensed matter, right? But very interestingly, the phases that people dreamed about and people theoretically considered very long ago, like this polar nematic phase and biaxial nematic phase, are being discovered very recently. So the liquid crystal field is not frozen in its state. It's developing very fast, very quickly these recent years. And so today I will very briefly describe to you these phases as well, right? So in a non-polar nematic, as I already mentioned, even if the building blocks can have polar nature, like these pentyl cyanobiphenyl molecules, the phase would have non-polar nature. So there is a head and tail symmetry. This is why the director has this double axis form, right? But in a polar phase, we can have vectors and polarization when all of these molecular dipoles point locally in the same direction. and building blocks can move around. And so recently, as I already mentioned, such materials have been synthesized, and they have a lot of excitement in the community. And there will be a separate dedicated tutorial lecture by Professor Mertelj, who is one of top experts in this research area, in January. So I will only tell you these phases exist, right? But I will focus more on the description of the phases discovered so far. And as a disclaimer, it's just impossible to discuss all of them within this tutorial lecture. So keep in mind, there are more, and the goal of today is just to systematically introduce the diversity of these different phases. And so why we are often so much excited about liquid crystals is that by applying very weak external stimuli, we can make big changes in their properties. So as an example, you can apply 1 volt electric field, right? And with that, you can reorient these little molecules. With that, the liquid crystal director deforms, and that changes optical properties, like, for example, light that is passing through such material. And because of this change of properties in our pixels of displays, we can control how much light is passing through. And with the help of additional help of color filters, we can display colors and display information. And here's an example of already from quite some years ago of a flexible liquid crystal display that can be pulled out of a pen like this and display information. But it's not the engineers and scientists who are really masters in using such anisotropic liquid crystalline properties. Nature did it long before us. And it's extremely surprising to find such liquid crystalline organizations in biology, in nature around us. An example is shown in here. So this is just a beetle that is utilizing such cholestatic chiral liquid crystal structure, where it has 3 slabs across the thickness of cuticle that allows it to reflect light with different circular polarizations, right? Left-handed, right-handed, or both at the same time. And there are different species of beetles that reflect one type or both, right? And you would imagine that while, being able to control polarization of light is something advanced, right? We have to go perhaps through PhD to understand how to do it and master techniques for that. But beetles, right, millions, hundreds of millions years ago, invented in the course of this of evolution these types of approaches. And so next week we'll have the 4 tutorials on applications of liquid crystals, right, where you will see how many useful things can be done with liquid crystals overall and chiral liquid crystals in between. And I guess the focus will be on engineered materials in that case. So I'll focus on liquid crystals today, but I want to put it in a bigger perspective of ordered states of matter. So Bart was telling us in 2 of his tutorial lectures a lot about crystalline solids, right? You remember there is a magic number 230 he wanted you to remember, right? And so the solid crystals have orientational and positional ordering. Now, there are plastic crystals that have positional ordering, but no orientational ordering. So in these types of materials, right, you could imagine on a crystalline lattice, right, unlike in a crystal, the little anisotropic blocks have well-defined positions in the centers of some periodic lattice, but their orientations are disordered, right? And so this is then a plastic crystal that has positional ordering present, but lacks orientational ordering, right? And then there are isotropic liquids that have no ordering at all, right? There are solid crystals that have both types of ordering, and liquid crystals are the types of material that have orientational ordering, but either no positional ordering or, as we will see in a little bit, have partial, only some degrees of positional ordering. So this is in a bigger perspective, right, of different types of ordered states of matter that we'll discuss. And so just kind of on this slide, you can see in relation to plastic crystals, which are counterparts of liquid crystals, right? As in liquid crystals, we can have different types of transitions between crystals, plastic crystals, isotropic disorder states, and so on, right? But as I mentioned, we will focus on liquid crystals today. So the liquid crystals can be of two different types. They can appear either in a certain temperature range as we are changing temperature. And so in that case, they are called thermotropic, right? And in this case, they would be composed of anisotropic molecules like these pentyl cyanobiphenyls that you can see in here, that will be either in orientationally ordered state or in a disordered state, right, in isotropic liquid. And you can have a transition between the two. So there is a temperature range within liquid crystals, within which liquid crystals are a ground state. In this case, these materials are called thermotropic liquid crystals. You can also have a lyotropic liquid crystal where the liquid crystallinity emerges as a function of concentration. And in this case, you could imagine you have something like water or a different solvent, and then anisotropic particles could be solid nanoparticles, could be some biological molecules or viruses, as we could see as well. And so in this case, very interestingly, orientational ordering can emerge as a result of maximizing entropy, right? So we often think, you know, maximizing entropy means more disorder, right? But under the conditions when you have some constraints in terms of volume that can be occupied by these anisotropic colloidal particles, and you need to maximize translational and orientational components of overall entropy, you can have this surprising behavior that maximization of entropy leads to liquid crystallinity. And so overall, there can be many different physical interactions that lead to liquid crystalline phase behavior. The two that I showed you in these classic examples of thermotropic and lyotropic liquid crystals, the two that are most common are the static interactions, or in other words, maximizing entropy for rigid rod-like anisotropic particles or other anisotropic particles, right? And another one is induced dipole-dipole interactions, which is nothing else but van der Waals interactions that for these highly anisotropic building blocks are anisotropic and lead to not just liquid state, but liquid crystalline state. And also many other interactions, such as hydrophobic, hydrophilic interactions, electrostatic interactions, and other can lead to liquid crystallinity. But coming back to this curious effect that entropy can have, right? I want to give a little bit more insight. We know that as I mentioned already, there are translational and rotational degrees of freedom, right? And so as we maximize entropy, we need to think about both components. So the number of states is related to the volume occupied by these particles. And so now, as we would imagine that two of these rods would be in orthogonal orientations relative to each other as depicted in here, you can see that there is a large volume excluded that for this second particle in here, that its center of mass cannot enter because of presence of this first particle, right? And because of that, if such particles are in a disordered state, the number of states that can be accessible to particles is smaller than if they are parallel to each other, as depicted in here, because the excluded volume in this case, due to presence of each particle, is smaller, right? And so then the second particle can take many more positions, right? From this simple illustration, you can see that the translational component of entropy favors orientational order. Of course, it's the opposite is true for orientational one, and the two compete so that once you have a large enough concentration of such anisotropic particles like rods or disks, the nematic liquid crystal emerges. What's interesting is that the liquid crystallinity can emerge for many different types of particles. And actually, some of the first observations of allotropic liquid crystals were done for the tobacco mosaic virus particles, right, which are very monodisperse rod-like colloidal objects, right, that would have about 18 nanometers in diameter, 300 nanometers in length. And you can see them in here on the leaves of tobacco, right? But if you would redisperse them into water at some concentration of these rod-like particles, you would see liquid crystalline phase behavior. For similar reasons, right, to maximize entropy, many other biologically derived molecules and particles can form liquid crystalline phases. For example, most important ones, of course, are DNA, actin, right? Actin, for example, is responsible for mechanical properties of biological cells. And in both cases, when we have either relatively short fragments of DNA so that it can be treated as rigid or semi-rigid rod-like particles, and also actin, again, in here, you can have filamentous actin of different lengths, but when the contour length is such that it's not much larger than persistence lengths, these types of rod-like particles naturally form liquid crystalline phases at appropriate concentrations. So the theory describing the transition from isotropic to a liquid crystalline state at some critical concentration was developed by Onzager some 70 years or 75 years ago. This theory predicts for particles with large aspect ratio, on the order of 100 or larger, the transition from isotropic to nematic state would happen at concentration that corresponds to 4 diameter over length or aspect ratio of these particles, right? And, this can, be very easily calculated for many different, again, biologically derived or synthetic nanoparticles. And it was found to work quite well. And so one can, for example, very easily estimate for the rods I was already showing, such as actin of different contour lengths or DNA. And we can see that at relatively dilute concentrations, not very high concentrations, we can already observe transition from a disordered state to an ordered state. Well, up to now, I was showing you mostly rod-like building blocks, but liquid crystalline phases can be formed by many other anisotropic building blocks, and the behavior of these phases is related to these blocks as well. So in addition to rods, we can have disc-like building blocks or banana-shaped building blocks, as well as many other shapes of molecules and nanoparticles can lead to liquid crystallinity. But the shapes, of course, define many properties of liquid crystal phases. However, we can have, for example, a uniaxial liquid crystal phase that would be formed by rod-like building blocks, such as the molecules you see in here, or disc-like building blocks. From the standpoint of view of point group symmetry, it's d infinity h in both cases. It's a symmetry of a rod or disc, right? But in one case, we have the average, the director is the average orientation of rod-like axis. In the other case, it's the normals to these disc-shaped building blocks. So up to now, we consider it just rods or discs, but the molecules that form liquid crystal phases can be chiral, right? And so this type of molecule that I told you is a classic example of molecules forming liquid crystal nematic phases, can have a chiral center, right? And so then instead of pentyl cyanobiphenyl 5-CB, we have another well-known molecules called CB15. And this phase, the phases that it would form would be chiral nematic phases. So what happens in this case is that locally, the material is very much like the nematic we looked at before. The rods, which have this chiral symmetry breaking, so not perfect rods, but locally would orient along the same direction. But as you would go to larger distances along certain helical axis direction, you would see them rotating with respect to each other. And so the length of these molecules is roughly 1 or 2 nanometers, right? The diameter is sub-nanometer, but the length, the distance or pitch over which they would rotate by 360 degrees typically would be in micrometer range, or tens or hundreds of nanometers, right? Much larger than the size of these molecules. And of course, it can be controlled from something on the order of 100 nanometers to infinity pretty much by simply mixing non-chiral and chiral molecules in different proportions. And so there is a simple relation for how this pitch would depend on the concentration of the chiral molecules in the mixture that you can use to calculate and define different values of pitch. So just like any other chiral object, right, like our hands, having these chiral centers, these molecules lack mirror symmetry, right? And therefore, we can understand this twisting behavior in the ground state of such a liquid crystal also from the standpoint of view of packing of such molecules within this medium. So up to now, I discussed liquid crystals with three-dimensional fluidity, which means their motions in three-dimensional space are unconstrained. The molecules can move around, the medium can flow, you can pour it very easily from one jar to another. But we can also have combinations of partial positional ordering with orientational ordering as well. And so in here, we see examples of so-called smectic liquid crystal phases that have the molecules organized into layers, where within each layer, they are free to move relative to one another. So it's not a solid, right? But they cannot easily jump across the layers. And so therefore, we can think about this type of medium as a one-dimensional quasi-long-range solid and two-dimensional fluid, right? Because in 2D, in planes perpendicular to director in here for smectic A type of phase, they can freely move around. So these types of liquid crystals flow, even though in a more complex way than isotropic liquids, but you can still pour them from one jar to another, right? And so oftentimes at low temperatures, we would have a crystalline solid. So somewhere here at low temperature, there would be perfect positional ordering and orientational ordering. But as you would increase temperature, you would perhaps melt it in stages. And first, for example, you could go to this smectic C state, right, that has molecules tilted relative to the normal, to the planes of the layers, but free to move relative to one another within the layers. And then as you increase temperature further, it can go to smectic A phase, where the molecules are also along the normal to the layers. And you heat it even further, it goes to nematic state, where there is no one-dimensional positional ordering, right? Only orientational ordering left. And you can already guess what happens as you increase temperature even further. It will go to fully isotropic state. So these type of phases are called mesophases for the reason that they occur in between the crystalline solid states and isotropic states, right? So the intermediate phases that occur in a certain temperature range within which they are ground states. The examples we looked at in here have rod-like building blocks, but they can be also made out of bricks, just like the biaxial nematic I briefly already showed you earlier, right? The building blocks of smectic liquid crystals, for example, could be brick-like. And in these two cases, the smectic C that I showed you before and smectic A that is made out of brick-like molecules, right? We have biaxial properties. So the orientational ordering can be defined along multiple axes, just like in the case of biaxial nematic we looked at earlier, right? So similarly, for example, in smectic A, we can have a director and B describing the orientational ordering of the shorter or intermediate axis of these brick-like molecular building blocks, right? Another variant of smectic C that we looked at in here, where the molecules are oblique relative to the layer normal. We could also have the Smalyukh CA or anticlinic version of it, where the tilting direction is alternating from layer to layer, right? And again, in this case, it's a biaxial system because we can define these different directions of tilt in addition to normals to the layers and molecular directions, average molecular directions. In the case of nematic states, we saw that chirality brings about interesting properties, right? That come from this mirror symmetry breaking at a molecular level. But what if the molecules that are forming spectic states, right, would also be chiral? Indeed, in this case, something interesting happens as well. So, for example, you could imagine that Smalyukh C state where the molecules are in here tilted relative to the layer normal, but then chirality would make them rotate on a cone as depicted in here, as you would walk along the normal to the layers. And again, you can define a pitch or a distance over which this rotation would be 180 or 360 degrees. What's additionally interesting in this case is that if your molecules have molecular dipoles, right, say, similar to the CN triple bond that we saw for pentyl cyanobiphenyl, then the orientations of these molecular dipoles will correlate in space, and therefore the material becomes ferroelectric. So we can define polarization of the material, and it will have response in a polar fashion of response to an applied DC electric field. So up to now, we looked at either three-dimensionally fluid liquid crystals or liquid crystals with one-dimensional quasi-long-range positional ordering. And I should clarify in here why I always say a disclaimer, quasi-long-range positional ordering, right? So it turns out that you cannot have a truly long-range positional ordering for one-dimensional solid crystals. It was shown quite early on by Landau and others that thermal fluctuations would destroy this positional ordering at very large distances. So what kind of distances we are talking about, right? So if you would go to something on the order of centimeters, right, you would not be able to correlate the centers of mass of these molecules, right? Because you would not be certain, where exactly the middle of that layer should be, right? You will lose a track because of thermal fluctuations. But on the length scale smaller than centimeters, you do have a positional ordering, right? So for many, of course, all practical applications, this is, one-dimensional solid for, for all the purposes of using such materials, right? And so now, up to now, it was 1D positional ordering, 2D fluidity. But let's play with dimensions a little bit more. We can imagine that we have two-dimensional positional ordering, like, for example, for the case of these disc-shaped molecules you see in here that are packing themselves into long columns, right? So in 2D, they are crystals. However, these columns can slide one relative to each other, and the centers of mass of these molecules are not fixed. They can move. This material still can flow, even though it would flow more like honey rather than water, right? Quite viscous. However, in this case, we have this interesting combination of two-dimensional positional ordering, which in this case is long range, truly long range, right? And then one-dimensional fluidity, right? And so orientational ordering is long range. In all of the cases we discussed so far, it's truly long range. But positional ordering in smectics was only quasi-long range. And here it's truly long range. But this is still a liquid crystal, not a solid crystal, because the material can flow. And in one direction, positions of centers of mass are not fixed. Yeah.
This molecule here looks like it has like a triangular symmetry, but you're treating it as a disk. Is there a reason for that?
Yeah, they would not be fixed all the time like this, right? And truly, these R's can be many different types of tails, right? So you could have longer, shorter hydrocarbon tails. You could put a lot of things in there. But just like I was telling you, for the pentyl cyanobiphenyl, by far it was not a rod or a cylinder for a chemist, right? They would say it's not, right? But from the standpoint of view of its organization and interactions with the other molecules, you can treat it that way. And then the symmetry of the phase it forms, has these properties. So uniaxial symmetry. So in a similar way in here, right? And we can have many different types of structures, right? These molecules, there is a huge variety of molecules that can form these nematic phases. So we often refer to nematics that are formed by disc-like molecules, discotic, and the ones that are formed by rod-like molecules, calamitic, right? And so as this columnar phase, so these type of phases are called columnar hexagonal phase would melt. As you increase temperature, you would get to a nematic state, right? That has no positional ordering, three-dimensional fluidity. And so, well, we just played with these dimensions of ordering and fluidity. And is this the end of the game? Can we do something else to get more diverse liquid crystal phases? And yes, there are many other things that come into play. So for example, again, as you have chirality and the tendency to form layers, what can happen is the formation of this twist grain boundary phase that you can see in here, where the blocks are smectic A-like, which means the molecules locally are perpendicular to layers. And then within each block that would have dimension of the order of 100 nanometers. So each molecule is by length 1 nanometer or 2 nanometers, right? Then the block is 100 nanometers, but then in between these smectic blocks, you have grain boundaries that allow them to twist one relative to another. Twist comes because of chirality, right? Given that tendency. And so then these screw dislocations, right, which are topological defects, will mediate this twisting behavior. And again, you can define a pitch over which they twist by 360 degrees, and that can be in a range of micrometers, right? And so these type of phases, right, can arise again in materials that have molecules with some chiral symmetry breaking. Another example of diversifying the behavior is formation of different bilayers or partial bilayers, right? So imagine these pentyl-cyanobiphenyl molecules or similar ones with tails on one side and CN groups on the other side. When they assemble into smectic-like layers, these molecular dipoles want to cancel each other, and so they form double layer or partial double layer type organizations. So, you know, while we looked at smectic A formed by individual molecules, it could be double molecular layer lengths, right, of these layers too. And yet another example, again, and here we have chiral building blocks, right, that can form these cholestatic or chiral nemetic phases I was showing you already and discussing with you. But under certain conditions, the molecules would prefer to twist not just along one axis, helical axis I was telling you about, but in all radial directions within this kind of double twist cylinder that I'm showing you in here, right? So as you would walk from its center to periphery, you will see it, the molecules twisting in all radial directions, right? And then on this double twist tube, you would see this barber pole-like configuration of the molecular alignment and director field. So now you realize that you cannot continue and fill in the entire three-dimensional space by such two-dimensional twisting, right? And so instead, what happens in these materials is that this twisting is terminated at about 45 degrees or so of this double twist tube. And then this, so as you would twist by 45 degrees from center to periphery, and then these tubes would pack into three-dimensional lattices. And that's not all. You get a cubic crystal-like organizations, right? But in between the tubes, you would see singular line defects running and connecting with each other. And now what's amazing is that this type of material, right, has these double twist tubes packed into body-centered or face-centered cubic crystals in the blue phases 1 or 2, or in a blue phase 3, they would be amorphous tubes, but you know, in still an anisotropical order at mesophase. And so then in these cubic phases, you effectively have the repeat units, right, of the double twist tubes, which we could think these days as two-dimensional fractional skyrmions as well, right? And you also have periodically ordered arrays of such singular line defects that arise between these double twist cylinders as we try to pack them. So these types of liquid crystals are naturally self-assembled photonic crystals. This is why, if you would look at them, you would see these beautiful selective reflection colors, right? Which come because of meeting the Bragg reflection conditions at certain wavelengths, which is comparable, visible light wavelengths are comparable to the periodicity you have in these types of phases. Okay, so we have seen that chiral mirror symmetry breaking, which can happen just because of presence, as an example of these chiral carbon centers, can lead to diverse forms of organizations, right? We saw the cholesteric phase or chiral nematic phase. We saw blue phases. We saw twist grain boundary phases. But what's interesting is that even when you have perfectly mirror symmetric building blocks, the chiral organizations can emerge at the mesophase state as well. And so the examples we discussed so far, right, would have this mirror symmetry breaking at the molecular level because of, say, this carbon center in here. But it turns out if you have molecules like pentyl cyanobiphenyl I was showing you before, but imagine taking that two such molecules and connecting them together, right, by tails, pretty much bonding them, right? Then you get a dimer-like molecules. And what is interesting is that the conformation of that molecule highly depends on the number of carbon atoms in between the two in this hydrocarbon chain. And so when we have odd number of these CH2 groups, we get this banana-like looking dimer molecule. And that's very interesting that when these molecules self-organize into liquid crystal phase, then they form chiral configurations. Moreover, these molecules would be on a cone, very much like in smectic C state, smectic C star phase that we discussed earlier, but in here there are no layers, right? And they would be rotating on a cone, and again, we can have certain periodicity over which these molecules rotate, right? So we can define this equilibrium configuration by, say, parameterizing the local director as depicted in here. And then in the limits, when this cone angle is equal 0, theta 0 is equal 0, we get the nematic phase that is non-chiral, right, that we saw earlier, just the rods are pointing in the same direction. In the limit when theta 0 is equal to pi over 2, we have a cholesteric phase we discussed earlier. And then at intermediate angles, we have the twist bend nematic state, right? And what's interesting is that this periodicity can be nanometer scale. Even the molecules are non-chiral themselves. The way they interact and self-assemble becomes chiral, and the periodicity in here can be sub 10 nanometers, 8 nanometers, 9 nanometers or so, right? So that makes it extremely interesting. And this, as well as ferronematic liquid crystal phase, will be part of dedicated tutorial by Professor Mertelj in January. Up to now, we discussed small molecules. They were a nanometer or two, right? And we also discussed some phases formed by micelles or nanoparticles. But the macromolecules or polymeric molecules can form liquid crystalline phases as well. And in here, there is a large variety of possibilities. So you could have main chain polymer liquid crystals where the building blocks are macromolecules that are made out of many small molecule units, right, monomers, connected to each other end to end. So main chain polymer liquid crystals. You could have side chain polymer liquid crystals where they are connected to a single backbone and exhibit orientational ordering as well. And you here have some examples, right? So the N stands for the number of the times you repeat, right? So typically can be hundreds, thousands, and much, much larger as well. And so all the phases that we discussed earlier, smectic, nematic, columnar, of different symmetries, can be formed by these polymeric molecules as well. The difference is that because these monomeric units, which are similar to small molecules we saw earlier, are now connected to each other, you would have different mechanical properties, right? So depending on molecular weight and the types of these repeat units, you could have them behave as solid or liquid, right, while exhibiting that orientational ordering. But as I already mentioned, from the standpoint of view of structure, everything that we have seen for small molecule liquid crystals can also be found in here. And we also know that a particular kind of polymeric systems that is very widely used technologically are elastomers, right, or rubbers of different kind. And you can have liquid crystalline elastomers as well. So in this case, these molecules are weakly cross-linked, and weakly cross-linked is very important because that allows these long chains to adopt many conformational configurations. So they can exploit different states, and therefore entropy can be large, right? You know, that would be important for their behavior. And so we are just like for the small molecules, liquid crystals earlier, we can have nematic, smectic, columnar phases, smectic C, smectic A, you know, all the different symmetries we had before. But because of having these molecules cross-linked, connected to some common chains, right, these monomeric units, now we can have interesting mechanical properties. And this combination of liquid crystalline ordering and properties of rubbers, right, that we integrate in here in a single system is particularly interesting because it can allow us, for example, develop artificial muscles, all kinds of actuators, and so on. And as we change orientational ordering, either degree of ordering defined somehow by a scalar orientational ordering parameter, or orientation of average ordering direction, we can control these properties quite dramatically. So, for example, in this illustration, you can see very dramatic effect that takes place as you would simply have this nematic rubber or liquid crystal elastomer, and you would change temperature. So as you change temperature, and originally, for example, you have it in a nematic state, and then you increase temperature, it wants to expand in direction perpendicular to director or average ordering direction and shrink along its axis because you're disordering these molecules, right? And so with that effect, you can achieve 300% strain as an example. And moreover, you can also switch director, and with that, you can actuate these materials. So light, electric fields, magnetic fields can be the external stimuli that allow you to produce these mechanical actuations. But now I would like to discuss with you how hydrophobic, hydrophilic interactions can also lead to liquid crystallinity. So many of you probably had breakfast eating something like cereal, where oftentimes you have food colorants, right? And these can form, if purified, liquid crystalline phases oftentimes as well, because they would often have, to give colors, such aromatic cores, and then some ionic periphery groups, like the ones in here that help these molecules to be dissolved in water. And so when such molecules would assemble in an aqueous medium, then they tend to hide their hydrophobic cores and expose their hydrophilic periphery ionic groups. And so therefore, they can stack on top of each other into these molecular aggregates that are one-dimensional molecular aggregates. So now you can imagine that the phases we discussed can be formed not just by individual molecules or nanoparticles, but rather than by molecular aggregates. So they can form nematic phase, where the centers of mass of these aggregates are not correlated, and they move around, but orientational ordering of these anisotropic molecular aggregates is well defined. They can also form columnar phases and many other phases. So now you just simply need to imagine that, there are these other classes of materials that can form liquid crystalline, give liquid crystalline behavior. Another example from daily life, right? We, of course, use soap and shampoo and in the morning, right? And these molecules that we use, right, to like soaps and shampoos, they typically have such hydrocarbon tails, and which are hydrophobic in nature, and then also hydrophilic groups, such as these ionic groups in here. And so therefore, the molecules have dual nature, amphiphilic nature, we call it. The head groups want to be exposed to water, whereas the hydrocarbon tails hate water and would like to hide from it. So very easily you can imagine that the properties of both head and tail groups can be satisfied when they form a bilayer, as depicted in here, so that the water-soluble groups, water-liking groups are exposed to water, and these hydrocarbon tails hidden within the bilayer structure. And so, as we would change concentration of these molecules, right, in a certain concentration range, we therefore can form these smectic-like smectic phases formed by such surfactant molecules. And I already mentioned that many molecules from our daily life have this structure. And in the right conditions, somewhere in between our hands during washing, there is likely some liquid crystallinity taking place. You're not perhaps detecting it, you don't have a microscope, but it's very likely the case. And so what do you need to observe this liquid crystallinity? So as you would have such surfactant molecules with amphiphilic nature, right, as we discussed, at very tiny concentrations, we would have individual molecules. And as you would increase concentration, right, the concentration of individual molecules increases. But then at some concentration, which is called critical micelle concentration, we get a lot of these micelles, as depicted in here, because they sense each other and start hiding the hydrophobic tails in the interior of these assemblies. As we increase it further, so in here we already have these micelles. these micelles can also take different shapes, right? So instead of being just spherical, they can become rod-like or other shapes, including brick-like, right? And so, and you can also form bilayers in the certain concentration range. And also many other configurations can take place, right, that satisfy this requirement of amphiphilic nature of these molecules. So by changing concentration of such molecules and also for different shapes of the surfactant molecules, where you can have either small head groups and large tail groups, or vice versa, small tail groups and large head groups, we can form a variety of different phases. So smectic phases formed by bilayers of these molecules, or columnar phases, or nematic phases, all kinds of cubic phases, and so on. And so here is an example of a phase diagram of one of the surfactants, right? That you can see at very low concentrations, the molecules, surfactant molecules are on their own, they're individualized. Then you have micelles, and then these micelles can self-assemble into different phases, cubic phases, columnar phases, smectic phases, nematic phases, and so on. And of course, you already probably thought about relation to biology as well, because in every single cell in our body, we have a membrane. This membrane is formed by lipid molecules that have that amphiphilic nature as well. And just like these bilayers of surfactant molecules that we saw before, this bilayer configuration emerges to hide the hydrophobic, water-hating tails in the middle and expose only water-liking groups of these lipid molecules to the periphery, to water. And so the most common type of phases that these lipid molecules can form is called L-alpha phase, where the molecules are free to move around each other, right? So it's a two-dimensional fluid, but of course they preserve this bilayer nature, which is very important, has very important biological functions, as we know. But if you would explore the phase diagram of these lipid molecules, you would see as you start at low temperatures, right, you actually can have crystalline phases of these lipid molecules, right, where you can have different types of positional ordering and different symmetries associated with them. As you would increase the phase, you increase disorder. As you would increase temperature, you increase disorder. And so, for example, the ripple phase can form. And then eventually L-alpha phase that has no positional ordering and short-range correlations. But in addition to temperature, many other molecules that can get into bilayers can change this behavior. So if you have just purely lipid molecules, right, there is certain temperature range over which they would have, you know, this smectic A-like behavior with two-dimensional fluidity and 1D positional correlation. But if you add, for example, cholesterol molecules, right, then the temperature range for this behavior is changing, right? And so we know very well that in biological membranes, we have many other molecules present, including cholesterol. And so this is very complex system, but behavior in many ways resembles that of one component analog of Smalyukh liquid crystal we discussed before. Many other phases can form as well when we have different types of biological molecules. So for example, you could have DNA and you could have lipid molecules, and then you form these kind of sandwich-like configurations, right? Or cake, depending which terminology you prefer, right? But you can see in here some examples of phases that have been discovered in such systems where you can have DNA and lipid molecules, and you can form these alternating layers. And this is just an example. Many, many different types have been discovered. And so again, as we think about DNA as a carrier of genetic information, right, within which genome is encoded, right, you think about a macromolecule like this in here. But if you stretch it, it becomes highly anisotropic block. Or if you have fragments of it that are comparable to persistence lengths, which is 50 nanometers for these molecules, right? You have formation of liquid crystal phases of different kind. And so as we already discussed, the biological membranes have lipid molecules, different types of other molecules like cholesterol, it's very interesting to make this connection between liquid crystallinity and biological functions. Many people pointed out that relation. And one example I'm giving in here, so I'll read it for you. Liquid crystals stand between the isotropic liquid and the strongly organized solid state. Life stands between the complete disorder, which is death, and complete rigidity, which is death again. So this combination of fluidity and ordering, you can see, is very essential in nature, including our own existence, right? But we can see, and we'll hopefully see over this course of the winter school from other tutorials that will come soon, that this combination is also extremely essential for many technological uses. And, the very long DNA molecules like lambda phage DNA, you can extract from bacteria, 16 micron or so in length. Once you stretch, can form very nice crystals that Bart could study, under polarizing optical microscope. But in this case, actually, we have only orientational ordering, and this birefringence comes from the combination of this orientational ordering and the properties of such DNA molecules. So also in nature, there are many other examples of orientational ordering that has biological functions. So in spider silk, for example, which is one of the strongest materials, we can have different types of liquid crystallinity involved, and you can see in here Smalyukh A-like organizations being depicted for you. But I will go through it very quickly because we are already past 1 hour. And I just want to perhaps give you a little bit additional insight in relation to different symmetries of liquid crystals that we can have. So we know that as we would look at this generic phase diagram, right, we have, for example, in here, this critical point between gas and liquid state, but there is no such critical point between the liquid and crystal phase in here. And so can somebody say tell us why this is the case? Could be the case.
Gas and liquid have the same symmetry.
Very good. Yeah, indeed, that's the case. They have the same symmetry, and therefore you can get to the conditions where you go through the supercritical fluid from one to the other, and you cannot tell apart whether you're in a gas or fluid. But if you have a liquid and a crystal with certain symmetry, right, then this can never happen, and you will have to break symmetry somehow, right? So, so we know very well that this symmetry breaking, can involve positional and orientational ordering from the examples that we discussed. And so when it comes to overall the different types of crystals that Bart very nicely discussed with us, right? The different types of crystals we can have depend on the symmetry of the basis and the lattice and combination of the two. And also they impose constraints on one and then one on another, right? And so that gives us, this variety of different space groups that we can have, the different types of solid crystals, right? How about liquid crystals? So in here we have seen that we do not need to have a lattice at all, because nematic liquid crystal can have fluidity in three-dimensional space, uninhibited fluidity. There are no lattice sites, right, to deal with. And so the examples that we looked at already include such liquid crystals as uniaxial nematic made out of rod-like building blocks with d infinity h symmetry, right? That's the symmetry of a cylinder. We also looked at the discotic nematic, and it's the same d infinity h symmetry in this case, as we discussed. The biaxial orthorhombic nematic that you can see in here has lower symmetry in the sense that any rotation around the director in this case brings the face into itself. You cannot tell apart the rotated version from its original version. In here, this will only happen when you rotate around certain axes, and three of them are mutually orthogonal, perpendicular to these faces of these brick-like building blocks. It will only happen when you rotate every 90 degrees around these different axes, right? Or when you reflect relative to mirror symmetry planes, which again, you can easily see, they are similar to the ones you would have for these brick-like building blocks. So therefore, the symmetry of this face in here is D2H. And I was telling you that this phase was so hard to discover until recently when it was demonstrated that it was called Higgs boson of soft condensed matter, right? But in fact, we can have many other phases as well that will have this property of combining certain point group symmetry of orientational order and no or only partial positional order. And so in here, you can see the examples of the symmetry breaking transformations that can happen, right? So the simplest one is that is very easy to imagine is when you have isotropic state, no order, you cool down that system and you get one axis of ordering. For example, imagine you had these brick-like building blocks, but only along one axis they are ordered and the others are kind of not keeping track of their orientations, right? So that would correspond to transition from isotropic state to the uniaxial nematic state. As you would cool it further down, you know, at some point, the other axis of the bricks can order, and you get to biaxial nematic state, right? But this is just one example of transformations that can happen for these blocks. There are many of these other different types. And again, different point group symmetries can be associated with nematic phases that we can form. The only problem, they all are possible, but they have not been discovered. And so for students and postdocs, that's fantastic news, right? Because Bart told us 230 is there, right, when it comes to crystals. And then here, in principle, there is infinity, but we only have a few. We have under 10 nematic phases, but infinity is possible. That's amazing news, I think. And many of them can be chiral. You can see many of them can be chiral. And again, in here, there are examples, like what would the building block look like? Which of them are found, which of them are not? Well, many are possible, few have been discovered. So I also have this link to the webpage on symmetry operations. And you could think about these different phases with different point group symmetries. And if you're a chemist, maybe you could think how to synthesize something that will form this phase, right? Or at least has it at the level of molecules. And also, there is a little procedure for you to kind of define the point group symmetry that, again, could be useful, right? But very importantly, I want to note, as I already mentioned before, the point group symmetries of the phases we discussed, right? There are many of them we found, right? For example, this is C2H, D infinity H smectic, D infinity H nematic. But when it comes to smectics, for example, well, you can have a huge variety of phases when the molecules are, of different symmetry, perpendicular to layers or tilted to layers. And again, infinity of possibilities. Will not be able to discuss all of them. Then when it comes to columnar phases, right, 2D positional ordering, well, that means 2D crystals, 1D fluids, and I showed you hexagonal, columnar hexagonal, but there are other 2D crystals we, of course, know, and the liquid crystals of columnar type with these symmetries have been also found and chemically synthesized, characterized, demonstrated. And then, of course, there are also quasi-crystals. Liquid crystal analogs of them have been demonstrated. I'm not able, due to time constraints, to discuss them, but there are elegant, beautiful examples of them. And so today, I just overviewed the structure of different phases of liquid crystals. But what will come next is the discussion of topology. So we know that several years ago, Kosterlitz, Solis, and Haldane got Nobel Prize, right, for their contribution to understanding the topology, the role of topology in physics. And one of the, papers that was quoted that was related to topological defect-mediated phase transition would look at how vortices of opposite charge can be generated, when thermal energy, for example, is strong enough to decouple them apart from each other, and that can mediate certain transitions, right? And so this is one example of why topology can be of interest, because it can mediate phase transitions, it can enable new types of phases. But also, as we will see from my tutorial next week, we can understand and define the different order parameter spaces that can be related to these different symmetries of the phases that we discussed, right? And therefore, then they can determine, these symmetries can determine what types of topological objects can be observed in these phases, including topological singular defects and topological solitons. And so during the next lecture, we will discuss the concepts of order parameter space and how we can determine it for different types of liquid crystals in particular, but also other condensed matter systems. And then how this determines all kinds of defects that can form in them, including knotted defects as well. Thank you.